Okay, so this is going to be somewhat of a bonus lecture. We found out in our last lecture that our model for modeling the velocity that a ketchup leaves a ketchup packet was terrible. The ketchup was going to leave at a velocity that was approaching that of the exit velocity of the Earth. And so it was 6.63 times 10 to the third meters per second, which at the very least is far beyond the speed of sound. So you would get a mini sonic boom for the ketchup leaving your ketchup packet, which is incredibly fast. And the reason our ketchup packet model was bad was because we assumed that our ball velocity was constant while squishing the packet. And it turns out this is a bad assumption because our pressure inside of the packet reached 3 times 10 to the 10th pascals, which is a truly ginormous pressure. And if we multiply 3, so our force, remember, is equal to our pressure times our area, is equal to 3.0 times 10 to the 10th pascals times our area, which is going to be equal to 4.5 times 10 to the 7th newtons, which is a truly gigantic force, right? And it's unreasonable to believe that our bowling ball, however heavy it is not going to accelerate in response to that force. So let's relax that assumption of our model. So let's assume that our velocity is not constant for our bowling ball. And if we do that, that means we need more equations in order to constrain our system, right? Because now we have an additional unknown, which is the velocity of the ball. So one thing we can do is we can solve for the velocity of the ball in terms of the solve for the velocity of the ketchup exiting the packet in terms of the velocity of the ball, which is going to be V exit is equal to V ball times length times width divided by A exit, all of this squared. And then we can plug this into our pressure equation. But then what are we going to do with our pressure equation? Well, we know now that we have a dynamic system. We have changing velocities, accelerating velocities. And the second you think that something is accelerating due to forces, you should apply Newton's law. Sum of the forces is equal to mass times acceleration, right? And so in this case, the sum of our forces is going to be equal to our pressure times our area, which is equal to mass times V ball times dV ball dx. And I'm using this formulation of acceleration as opposed to the one you're used to, which is dx squared dt squared, because it makes that math easier to solve, period, right? So the result we're going to get requires a little bit more mental effort to interpret, but that's not a big deal. As you'll see, it actually is really pretty stark results. But like I said, because we've substituted in a linear differential equation as opposed to a second order differential equation, it makes it a lot easier to solve. Okay, so if we have P times A is equal to mass times VB times dVB dx, we can substitute our pressure, which we have here in terms of V exit. Oops, right here. This is V exit right here. For our pressure, and this is a packet. This is the 3 centimeters by 5 centimeters area that the ball is in contact with the packet. So this is going to be equal to rho times V ball times length times width all over A exit squared times length times width. Remember, that comes from here where we rewrote the V exit in terms of V ball. And that's going to be equal to our mass, which is our mass of our ball, times our velocity of our ball, times dV ball dx. So this is assuming that the ketchup packet doesn't explode. So again, we're making an assumption. We've got to state these assumptions. This assumes that the packet does not expand or explode. Okay, so assuming that's true, like we have a Kevlar ketchup packet because, I don't know, we're super rich. We can solve this differential equation because we have v ball squared on the left, v on the right, dv dx. We can easily solve this differential equation. So let's do that. We have rho L cubed W cubed over A exit times 1 over mass of our ball times dx is equal to 1 over velocity of our ball, dv ball. And you've done this integral many times. This is equal to, when we integrate it, c times e to the, x is equal to, v ball then is natural log of v ball is equal to rho L cubed W cubed over A exit times 1 over MB times x plus c, which when we raise to the power x, we get that v ball is equal to c times rho L, c times e to the rho L cubed W cubed over A exit times 1 over M ball times x. And we can solve for this c, and we find out that that c is just equal to the initial velocity of the ball. So v ball is equal to negative 4.42 meters per second times e to the rho L cubed W cubed over A exit times 1 over M ball times x. And what's really interesting is this allows us to solve for the exit velocity of the ketchup in terms of the velocity of the ball. Because remember, we can easily exchange between the velocity of the ball and the velocity of the ketchup. And so I've done that here. So we can see that the exit velocity of the ketchup, when the ball initially hits the ketchup packet, is approximately 7,000 meters per second. Outrageously high, right? Outrageously high. But then before the ball even compresses the ketchup packet more than 6 microns, the velocity of the ball has fallen quite low. And by the time we hit 10 microns, the velocity of the ball is basically zero on this plot, right? So it's probably a few meters per second, but not anything significant. And 10 microns is very small. The width of your hair is 100 microns. The width of a blood cell is 5 to 10 microns. So before the ketchup packet has moved the width of a cell in your body, it has slowed down tremendously, right? And the exit velocity of the ketchup has slowed down to on the order of probably meters per second, right? Which is why when you see ketchup packets that people have stomped on, the ketchup goes a couple meters maybe, but not much more than that because the ketchup velocity actually isn't that high. It's very high at the beginning, and so the question is why do we not hear a sonic boom when we first step on a ketchup packet? And the reason is because our model still isn't that great. We can improve our model more by including gravity. We could include the bursting of the packet. Assume that the material has some sort of yield strength and solve for the stress in the actual packet material and whether or not it'll burst. We can also include elastic deformation of the packet, which means our volume would change in a very complicated way with time. But what it would do is it would allow a smoother transition to a slower velocity for the ball and a much lower initial velocity of our ketchup packet, because instead of the ketchup exiting at multiples of the speed of sound, like an order of magnitude greater than the speed of sound, the ketchup will start exiting at a normal velocity, but the ketchup packet itself will deform and expand in order to accommodate that increase in pressure. That pressure energy, in other words, is not going to be converted 100% into exit velocity of the ketchup. It's going to be converted into expanding the ketchup packet itself. So there's lots of ways we can improve this model, and we could keep doing this for weeks until we can accurately model the velocity that ketchup exits a ketchup packet. But hopefully this gives you an idea of how you might start with an easy, simple model and slowly increase the complexity.